Welcome to a quick follow-up to the in-class lecture on special relativity. This stuff's pretty weird. Hopefully you're gonna sort of soak in it for a little while and figure out how well you're understanding it and give me a chance to help you if you are not. So I'm jumping in here with some supplementary issues, some things we need to talk about, but I'm not going back over the heart of special relativity. You've got my notes on that, you've got access to the lectures on Echo 360, and you've got access to me if you have some questions about that. I want to connect special relativity back to some issues we've talked about measurement and meaning. One of the things I've emphasized in class about special relativity is there's nothing really experimental about the paper. It's a proof. It's a consistency proof. So it is logic, it's math, it's philosophy, it's also physics. But it really just tries to show you what you're committed to if you try to preserve Galilean relativity and the principle of the constancy of the velocity of light. That's all he tries to do, is show you the effects on measurements of space and time, excuse me, if you try to preserve those two principles. This move of Einstein's was extremely influential in philosophy of science in ways we're not going to really have time to go into. It launched a movement called operationalism, which was still very much in vogue when I was in high school in the 1980s anyway, which identifies the meaning of scientific terms with measurements, with observations, with measurement operations. The inspiration for this is special relativity. Einstein shows that you don't mean anything by asking questions about space or time if you can't tie them to measurement. There is no measurement you could perform to figure out whether two events are, scare quotes here, really simultaneous. The only measurements you can perform are about what time it happens in one reference frame and what time it happens in another reference frame. And so many philosophers of an empiricist bent, and psychologists too. If you ever studied behaviorism in the history of psychology, that's very much in this spirit, wanted to discipline scientific meaning in terms of measurement. And Einstein's super important for this, right? He really does try to show you that you're led into kind of meaningless metaphysics about how long something really is. Whether that's a measure of length or the length of someone's life, there's no answer to that question. There's only all the answers in all of the reference frames. Nevertheless, we've already seen that there are issues about the limits of something like operationalism, because you can't always identify a magnitude with its measurements. I think we talked about academic merit, which you can't just use like SAT scores, because those are not particularly good predictors of how people are going to do in college. SAT scores plus high school GPA might be better, might be worse, but in any case, those are proxies. Those are attempts to substitute a measurement that we know is imperfectly correlated with the magnitude in question. Same thing with bad cholesterol and heart disease. So we often substitute a measurement because it's a cheap and economical and efficient way to get a grip on the thing we're really interested in. I want to distinguish those cases from this case. What Einstein shows is there's nothing more to space and time than all the possible measurements of space and time. So it's not that we're using a measurement of space or time in our reference frame to try to get at space or time themselves. There is only space and time as they would be accurately measured in every reference frame. So this case, and it's an interesting philosophical issue, how to sort cases where you do want to say the thing has reality apart from the measurements, and cases where you don't. But this particular move of Einstein's has, to this day, been influential in the practice of science and in the philosophy of science, because it shows the dangers of not linking your scientific claims closely to measurement. There are dangers in the other direction. You could overlink them and think that SAT scores are a measure of something they're not. But in special relativity, the real danger is thinking you mean something when you can't at all measure it. So this is something, as you go through life, you want to get a somewhat sophisticated understanding of. Now we turn to a different issue, another aspect of special relativity that is not relative. Normally, the term we would use is invariant. The speed of light is invariant, not relative. So is the space-time interval. This is due to one of Einstein's math teachers, a guy named Hermann Minkowski. So the first thing you need to do is get a handle on this notion of space-time. It's hard to picture 4 dimensions, but all we really need to do is assign values to 4 dimensions, and we actually do this all the time. If this were pre-COVID and you wanted to have a meeting with me in my office, you would need 4 numbers, at least implicitly in your head. You need the latitude and longitude of my office in Eddy Hall. Obviously, you don't get there by using the latitude and longitude, but you need an equivalent. You need to locate the building. The third number will be, as it were, the z-axis, the distance above the surface of the Earth. My office is on the 2nd floor, but you also need to know when. So without being able to provide some values for 4 different magnitudes, you wouldn't be able to meet me for office hours. So you navigate 4-dimensional space-time all the time. Again, depending on your powers of imagination, it can be hard to graph it, but it's not that hard to understand it. Minkowski's space-time allows us to calculate an interval. It's a distance between 2 events, but it's not a distance in space, nor is it a distance in time. It's a distance in space-time. So all observers moving at constant velocity will agree about the distance in space-time between 2 events, but they might divide it up somewhat differently among the 4 dimensions. So this is another way of appreciating the ways in which measurement is tied to a particular reference frame, but that there's a real world not constituted by our measurements. This is the kind of realist push that goes along with the insistence on measurement of magnitudes. Sorry, this is hard stuff to explain clearly. I'm going to try to explain this in somewhat different terms, but really all you need to do is envision that in a 4-dimensional construction, you could, as it were, draw lines between 2 events, and all observers would measure them being the same length, or curves, really, not lines. But it's in 4 dimensions, not in 2 or 3. And so a more down-to-earth way of appreciating this is also a way of giving your parents some grief if you go home during Thanksgiving. If you're sleeping until noon and they give you grief, tell them that you are moving at the speed of light. Everything is moving at the speed of light. Why does it not seem that way to us? Because everything is moving at the speed of light, not through space, but through space-time. We all have essentially light speed, but we divide it up among the 4 dimensions differently. Mostly we spend our speed through space-time through time, which is to say we age. At the other extreme is light. Light is moving as fast as anything can move and all along one axis. So it attains maximum speed along that axis, and it doesn't travel through time at all, so it doesn't age. All objects that are at rest relative to us age at the same rate we do, but things that are in motion at a significant fraction of the speed of light with respect to us will not age at the same rate we do. So this is really no different than if you and I both start in the center of a Cartesian coordinate system, and you run along the x-axis at 5 miles an hour, and I take a 45-degree angle. I bisect the x and the y-axes. We're going at the same speed, but you will travel farther down the x-axis. I'm going just as fast as you are, but I'm dividing my speed among 2 dimensions. That's how it is with everything in the universe. It is moving at the maximum speed, but dividing the speed among the 4 dimensions differently depending on from where it's measured. So, As we wrap up special relativity, and this is another opportunity for you to take stock and see how well or how poorly you think you're understanding this stuff, I want to leave you with the problem that Einstein is confronting in 1905 into 1906 as he finishes this paper. He realizes special relativity and Newtonian physics are incompatible with each other. The reason is there is no role for time in Newton's theory of gravity. Newton's theory of gravity says everything in the universe pulls on everything else in the universe. The numerator is the product of the masses. The denominator is the square root of the distance. There is no time. It is instantaneous action at a distance. Special relativity, though, says nothing can travel faster than light. So there can't be instantaneous action over these gigantic distances. And so Einstein knows he has to wrestle with Newton and gravity. And he spends the better part of the next decade wrestling with Newton and gravity, which is going to allow us to generalize special relativity to objects that are moving at something other than constant velocity with respect to us. We're going to start dealing with accelerated motion, just as we did back with Newton and Leibniz. You first look at constant velocity motion, and then it's going to take different mathematical tools and a different framework to confront accelerated motion. All right, you'll see that later this week. Thanks for your time and attention.